So today we're very happy to have Yacobi from Sydney, who will tell us about on the action of vowel groups on canonical basis and categorical braid group action.
All right, thank you for coming to my talk. Yeah, so what I'm going to talk about today is joint with my undergraduate student, Martin Gastow, who has just completed his undergraduate degree at the University of Sydney. All right, so I want to start with just telling you kind of the basic setup and the kind of problem that I'm interested in, and then I'll get into a bit more details. The setup is as follows. I have some finite group, let's say W. For me, is always going to be a vowel group, but for the purposes of the current discussion, it's not so important. And I have a representation of this group on some vector space V. And I'm interested in situations where this vector space comes equipped with some canonical basis. Let's call it V. Some canonical basis, usually of geometric origin. Okay, so this is the kind of setup I have. And in this situation, if I take an element of my group W, I can consider the matrix, which is the matrix of W with respect to this basis, right? So this is just matrix of this operator W on V with respect to B. Okay, and the kind of question that I'm interested in is following: can we extract some interesting let's say combinatorial information about this canonical basis from this matrix? It's a very kind of explicit question, but if any of you guys have experience working with canonical bases, usually their formulas are quite complicated, and taking a general element of the group and wanting to express its matrix and its basis in some nice way is kind of a hopeless problem in general. But like the main theme that I want to try to communicate today is that for many W and for many representations that have naturally occurring canonical bases, for many elements of W, this is actually quite possible and quite interesting. But not for all elements of W, it's going to be some special classes that come up. Okay, and this is going to be, and we'll see how to relate this to some interesting combinatorics with the bases. So that's the kind of setup, and in the outline of the talk is I'll spend like probably half the talk talking about sort of the most interesting example, which is that W is a symmetric group, V is an irreducible representation, and B is the quasi-journalistic basis. And I'm going to describe some history of this problem, like not the first ones to think about this, in this setting. And I'll describe our most general results for this setting. And then I'm going to tell you how we prove these results. And this is going to be the next part of the talk, which is really about braid groups acting on triangulated categories. And finally, at the end of the talk, probably just a little bit, I'll talk about how to generalize the story. It'll become clear to simply laced vowel groups, and where V is going to be zero weight space of an irreducible representation. Irreducible representation of the corresponding group. And B will be the dual canonical basis in this setting. So everything I'm going to say in the first part of the talk has direct generalization to this level of generality. Okay, so that's what I'm going to talk about. All right, so let's start with part one. So yes, I'm going to consider the setting of a symmetric group. So let's take lambda, a partition of n, and to such lambda, we associate the corresponding irreducible representation. I'll denote it S upper lambda. This is usually called a spec module. So I'm always working over C here. So this is the irreducible representation corresponding to lambda. And there's some, of course, these are very well studied. We know a ton about them. Excuse me. One thing we know is that we have a nice combinatorial interpretation for the dimension of these modules. This is counted by the set of standard Young tableau of shape length. Right, so this is my notation for standard Young tableau of shape lambda. So just in case you're not familiar with this, so for instance, suppose I look at the representation, say 3, 2. This is an irreducible representation of S5, and I want to compute its dimension this way. So I need to write down all the possible standard Young tableau of this shape, 3, 2. And so we can start doing it. We just enumerate it. So here's one standard Young tableau. Remember, a standard Young tableau is a failing of the diagram with the numbers 1 through n, which are increasing along the rows and down the columns. So here's 1, and then 1, 2, 4, 3, 5, and 1, 2, 5, 3, 4, 1, 3, 4, 2, 5, and 1, 3, 5, 2, 4. So that tells us that the dimension of this irreducible representation is 5. Okay? And a fact that I'll be relying on in this talk is that we have a canonical basis for these representations, right? So the setup is that the Kaja and Lustig basis, let me just abbreviate that KL, of the Hecke algebra descends to a canonical basis of these spec modules. Now, to note this basis, C lower t, this basis is naturally indexed by exactly the combinatorial object expected to be indexed by standard Young tableau. And this is really a type A phenomenon. So Kajan and Lustig define a basis of the Hecke algebra and other types, of course, and this descends to a basis of the cell modules of the Hecke algebra and all types. The thing that happens that's special in type A is that these cell modules are irreducible. So we get a basis for the irreducible representations, and I'm just now setting q equal to 1 and just forgetting about the quantum parameter. Okay. And this basis is interesting from many points of view. So the Cauchy basis, so let's say, has interesting connections. We could probably list a whole bunch of stuff, geometry, where we talk about intersection theory of Schubert varieties, representation theory, if you want to compute multiplicities of simple modules inside Verma modules for the corresponding Lie algebra, combinatorics, it's closely related to the RSK correspondence, for instance, and there's a long list. Okay. All right. So let me tell you the sort of the first results along the lines of what I'm interested in. This is from the mid-90s. So this theorem is due to Berenstein and Zelebinsky. And independently Stenbridge from 1996. And they prove the following results. They say, let's consider the long element of the symmetric group. Then for any lambda and any standard Young tableau shape lambda, the action of this long element on the causalistic basis is amazingly nice. It's up to sign another causalistic basis element called E of t, where E is called the evacuation operator or Schützenfeld evolution on tableau. So I mean, if you just sort of look at the definition of, you consider the definition of the causalistic basis and the action of the symmetric group on it, there's no reason to hope that you can pick some element in the formulas for its action are going to be so nice. But it turns out that for the long element, it's amazing. Another way to say this, of course, is if I take this long element and consider its matrix with respect to the causalistic basis, I get a permutation matrix of this in science, right? So, forgive me for the next part of this talk. I just want to tell you a little about the combinatorics that's happening here on Tableau, even though it's maybe not the main point, but I just want you to get a sense of the combinatorics that's being encoded by this action of the long element. So I just wanted to I want to tell you what the evacuation operator is. But first I need to tell you what the promotion operator is. So the promotion operator, so this is, I'll call it P, this is an operator on the set of standard Young tableau. And I'll just give you an example. So suppose I start with this standard Young tableau. That's the shape 3, 2, and I have 1, 3, 4 in the first row, 2, 5 in the second row, and I want to apply P to this thing. You do what's called the jeu de taquin moves on the tableau. You play this game. So how does this work? You take your tableau and replace the long element, the biggest entry by a dot. And then the game is you want to take this dot and move it into the northwest corner. And the moves you're allowed to make are up or left. And if you can do both, you always go in the direction of the bigger entry. So in this case, this dot can move up or left, but it's going to go up because 3 is bigger than 2. And so then I get 1, 2 dot, 1 dot 3, 2. And then now I can only move left. So I go like this. And now I'm done because I've moved the dot to the top left corner. And now you replace your dot by 1 and add 1 to every other entry. And that says that promotion of this tableau is this tableau. That's how you define promotion. And evacuation is based on promotion. So evacuation, E I'll also just tell you by giving an example. Suppose I start with a tableau, let's say 1, 2, 3, 4, 5. Okay, I want to apply evacuation on this guy. The first thing I'm going to do is apply inverse of promotion, which is sometimes called demotion. Okay, but it's got a negative connotation, so I don't want to say that too much. And so if you do this, I did this ahead of time, so you don't have to worry about it. You get this guy, and then what you're going to do is you're going to fix the biggest entry. So this 5, and this 5 is now out of the story. We're going to fix it here, and then you apply the inverse of promotion to what's left over, and so you're going to get 1, 3, 2, 4, 5. 5 has already been fixed. Now I fix the next biggest guy and keep on going until everything is fixed. And at the end, you'll get 1, 2, 5, 3, 4. And that's how you define evacuation. Okay, so this is the combinatorial structure, the action of the long elements on causalistic basis is encoded. All right. Good. So this is, again, as I was saying, this is from the mid-90s. I want to tell you another result of similar flavor that's much more recent due to Brendan Rhodes. So this is a theorem from 2010. And it says the following. Instead of considering the long element, consider the long cycle, what we call the long cycle. So let's see, this is cycle 1 goes to 2, 2 goes to 3, so on. A particular Coxer element. And let lambda be a rectangular partition. So now this is already different from the previous theorem where there's in this first theorem there's no limitation on what shape lambda we're considering. Here we're only considering those partitions where the known diagonal looks like a rectangle. And then Rhodes' result is that for any tableau of this rectangular shape, the action of the long cycle on the casualistic basis is up to sine another casualistic basis element, but this time the long cycle is including the promotion operator. Okay. I want to make two remarks about this. One is that this was the essential new result in Rhodes's cyclic sieving phenomenon. For the action of promotion on the set of standard known tableau of some rectangular shape. So cyclic. So if you're not familiar with this notion of cyclic sieving phenomenon, what I'm essentially saying is that Rhodes was trying to study. Okay, you have some automorphism of the set. He was interested in the cycle structure of this automorphism. And the cyclic sieving phenomenon is a particularly elegant way to encode that information by saying that the cycles can be, the number of I cycles in this permutation can be obtained by taking a cubic length formula and evaluating it at an iterative unity. So it's two interesting things. And there was one new result he needed to prove that, which was this theorem, and then he combined some more results together. The other remark is that this theorem is false if lambda is not rectangular. And it's not easy, it's not hard to write down examples. Okay, so what I want to tell you now is, I guess, our first result, which is how to generalize this to arbitrary lambda. So let me just record some notation. So if we fix some partition, lambda and n, let me denote by square brackets WKL to be the matrix of W acting on this lambda and KL basis. Just a notation. And so the theorem is as follows. So now we say let lambda be an arbitrary partition. We don't require the strict singularity condition. And here's something that's going to seem kind of strange. Consider the QR decomposition. So I take the action of the long cycle. So I take the matrix obtained by the action of the long cycle on the casualistic basis, and I write it as a product of an orthogonal matrix times an upper triangular matrix. Right? Something we all know from every time we have to teach them in algebra, we have to remember what this is. Right? So we consider this QR decomposition. Then Q is the generalized permutation matrix for permutation. So in general, if you take an arbitrary matrix and write its QR decomposition, of course Q doesn't have to be a permutation matrix. So something very special is happening for these matrices where this is a permutation matrix up to signs. That's what I mean by generalized. Those are minus ones. And this permutation matrix is exactly the permutation matrix for this promotion operator on tableau. Okay, so this is how to generalize this story. Another way to if QR decompositions, if this is kind of like maybe not the easiest thing to understand, another way to write this that might be more familiar is to say that if I take the action of the long cycle on casualistic basis element, then up to sign, I have this thing, plus some lower order terms, which you can express as this. This is another way to say it if you don't want to mess around with your organizations. That I can have some ordering on the tableau, it's a Brew order. And up to the leading term is exactly capturing this promotion operator, and then I have some junk in lower order terms. Okay, so that's okay, that's our first result. And if you look at this theorem and compare it to the previous theorems, you might ask, like, what's special about the long element in the long cycle? Why can we get this nice, interesting combinatorics from these two elements? So the answer is that they're so-called separable permutations. This is a notion from combinatorics that I've only discovered in doing this research. I had not heard of it before this, but the definition is quite natural. So let me tell you what a separable permutation is.
Can I ask a small question?
Yes.
Yeah. So first of all, sorry for getting here late. When you write the QR decomposition, you have a specific inner product in mind. I mean, there is some kind of canonical inner product on V lambda.
I mean just orthogonal, like in the usual matrix sense, like Q times Q transpose.
But the transposition is not a canonical operation; it's only canonical in the basis. So you mean in the basis? So you
That's right.
In the KL basis.
In the KL basis. Yeah.
Okay. Yeah. Fair enough. Okay.
Good. Thank you. Right. So what does separable mean? So if I take two permutations, say W1 is a permutation in Sn, W2 is a permutation in Sn, I can combine these in two ways to get a permutation in Sn plus n. One is called direct sum of these permutations, and this is given by, the easiest way to describe this is just writing down a permutation matrix. I just take the direct sum of the permutation matrices for W1 and W2. I get another permutation matrix. This is an Sn plus n. And the other thing I can do is take the skew sum of these permutations. So according to Wikipedia, this is the notation for this thing. And here in permutation, in terms of permutation matrices, I just put these guys on a skew diagonal, another permutation matrix. So that's operations. So then we say that W in Sn is separable if it can be obtained from the trivial, the trivial permutation S1 by a sequence of direct sums and skew sums. So, for instance, if I start with, so I have this trivial, I have this permutation in S1, very trivial thing. I can take its direct sum, I get the identity matrix. I can take its skew sum, I get the transposition. Now I go to S3, I can combine these matrices in arbitrary ways using direct sum and skew sums. Now I go to S4 and I keep on going. Like all possible permutations I can get this way. So in S2, clearly you get everything. You guys can convince yourselves. In S3, you get everything. S4 is the first place where separable permutations are not all permutations. So, so let me just write some examples here. Sorry. So I kind of just want to write a non-example more than an example. This in cycle notation, 1 goes to 2, 2 goes to 4, 4 goes to 3, and S4 is like the first non-separable permutation. You can't write it. You can't write it in terms of these operations. But these class of separable permutations grows exponentially. But of course, in a limit, exponential or factorial goes to 0. So they're not most permutations in any way. But there are a large class of permutations. And the claim, and by the way, I should say examples of separable permutations include W naught and C. These are and the claim is actually that this theorem that Martin and I proved goes through for separable permutations, all separable permutations. So maybe I should just. I'll be right over here. Is that again, lambda is arbitrary, and now let's take W and Sn separable, and consider this QR decomposition. So again, I'm taking the matrix of W with respect to the KL basis, and I'm taking this QR decomposition. Then almost exact same result. Q is a generalized permutation matrix for some bijection, which I'll call phi sub W. Now this bijection depends on W on the set of standard Young tablet. And of course, the natural question is, what is this bijection that you get? And we can say explicitly what it is. I don't want to get into that level of technical detail, but this, I'll just say phi W is controlled by the cactus group, something called the cactus group. So the set of standard Young tableau has a known action by a group called the cactus group, and that's exactly where these bijections come from. And if you give me a separable element, I can pretty easily tell you exactly which cactus group element it corresponds to. But like I said, I don't want to go into that detail. It's going to take a little while to explain. Okay, so this is the end of the first part of the talk, where I kind of just tell you what the results are in type A. And now I want to talk about how we prove them and what's the techniques underlying this. Of course, if anybody has a question, please let me know.
Yes, so you're not going to get into detail on the cactus group thing. So is there any, can you see a way to generalize this for non-separable with on the cactus group?
No, I think it only holds for separable elements. I think this is key.
Okay.
I can't prove that yet, but looking at examples and from the techniques that I'm about to tell you about,
Yeah.
I think it's like, let me just say a conjecture. This type of results only hold for the class of separable elements.
Oh, sorry, is there a combinatorial interpretation of this function? Like the,
Yeah, this characters group is totally combinatorial.
and its action on Tableau is also combinatorial?
Yeah, it's all partial shoots inverse evolutions and
Okay.
compositions of them.
Sweet.
I don't want to steal your thunder, but maybe look at this, but is there some geometric characterization of the separable elements? or-
So there, yeah. So separable elements have been studied by combinatorial community for a while. They're studied from like a pattern avoidance point of view. So like there's the permutations that avoid this pattern, and another one is like the transpose of this one are exactly the separable permutations. And I was hoping that would lead to some geometric connection, but I haven't discovered that one exists yet, like about singularity theories and stuff. I don't see anything like that. But they are like, so for instance, the number of separable permutations is counted by something called a Schroeder number, which if you know about like, you know, how you count Catalan numbers by paths on a grid that go up or right, that don't cross the diagonal. If you also allow up, right, and diagonal steps to go from 0, 0 to NN without crossing the diagonal, that counts Schroeder numbers. That's what counts as separable. But to answer your question, I don't really know too much. Yeah, I mean, I think there should be something, but I don't know. All right, so now I'm going to generalize this story, and I'm going to tell you, well, no, I'm going to tell you what's underlying these results. So now let's consider a simply Wesley algebra. And let's denote its beacon diagram by I. And a major play here is going to be the braid group corresponding to this type. So this is and this has a presentation of generated I'll call sigma I. Let's satisfy the braid relation. So sigma I and sigma j commute if I and j are not connected in a Dicke diagram and are satisfied the other relation. Sigma I is equal to sigma j, sigma I, sigma j. If they are connected, that's the braid group. And I also need the vowel group. So the vowel group I'll call W. And the I'm going to consider this presentation with generators SI. These satisfy the same braid relations plus the quadratic relations. Okay. So, all right. All right, so I have this set up, and now what I'm interested in is a categorical representation of the quantum group associated to G. So I'm going to take C, this is an abelian linear category with a UQG action. So here I really mean in the sense of Cabana, Flat, and Rouquier, and what I'm not going to go into all the details of what exactly this entails, but what's the basic idea is that, okay, first of all, we have a decomposition, a kind of weight space decomposition of this category. So I have decomposition like this, where X is the weight lattice, G. That's something I need. I need exact functors, like for instance, EI1 mu, this is a functor that goes from C mu to C mu plus alpha I and another functor fi that goes from C mu to C mu minus alpha. This is all just structure that kind of mimics what a representation of a Lie algebra is. And to satisfy there's a whole bunch of other data that we need, and to satisfy some relations. But what are some important things for us? Well, first thing we want is that from this data, we can define an action of the quantum group on the complexified Grothendieck group of this affinity category. Okay, so this, so first of all, this decomposition of the category here gives me a decomposition of this complex vector spaces into the direct sum of spaces. That corresponds to the weight space decomposition of this representation. So that already tells me how the Cartan part of the quantum group acts. And these functors, which I said I didn't write down, but I said are exact functors, these induce operators on this vector space. This gives me the other generators of the quantum group, and they have to satisfy the quantum group relations to actually give me an action of the quantum group. So that's one thing we want. That's like the very least. We need some bijunctions. Relating this EI and FI functors. And finally, we need something called a KLR algebra action on compositions of these functors. So if I take some, let's say, EI functors and compose them in some way, I have an action of some algebra called the KLR algebra on this functor. And again, I don't want to go into all the details of exactly what these things are. There's one thing I do care about, which is that from all this data, Schwang and Ruquier construct the so-called Ricard complex. Now look at this theta I. And this is a functor, a triangulated functor from the bounded derived category of C to itself. Okay, and I guess the point I'm trying to make here is okay, so we started with some category C, and I'm ending up with some end-loop functor of a corresponding bounded derived category. And to construct these functors, you need all the data that I wrote here. So for instance, these functors these theta I are constructed as complexes of functors. Each entry in the complex comes from these EI and FI, but you need this KLR algebra action too to construct the entries in the complex because it needs divided powers. So you need this KLR algebra just to construct the terms in the complex. The data coming from these adjunctions tell you how to construct the differentials of this complex. So you really do need this higher structure that's very non-classical, the categorical structure to construct these functors. Okay, that's just the point I want to make. And here's the main theorem about them. One, this is due to Schwang and Ruquier. Which is that these guys are equivalences of triangulated categories. This is the main result that Schwang and Ruquier needed in order to prove the Brouillet's conjecture for symmetric groups. And two, this is due to Callis and Kamnacher. It's that these functors braid. So we have an action of the braid group on this bounded derived category by the assignment that the generator sigma I goes to the functor theta I. Right, so that means that theta I satisfy these relations in the braid group. So theta I, theta j is isomorphic to theta j, theta I when I and j are not connected, and we satisfy the non-trivial relation when they are. Okay, and my focus for this talk is going to be the resulting braid group action on what I'll call DBA, or here A, just to save myself writing this all the time, is just the zero weight subcategory of C. So it turns out that this subcategory is preserved by this B action. So this thing is just a piece of this bigger one, but it's preserved by the B action. I just want to focus on that one. And this is just this restriction is only to make my life easier. It's not totally necessary. How much time do I have?
20 minutes.
Okay, great. Okay, so now, for an element W in my bounds of W, with reduced decomposition, say SI1 dot SIR, so reduced decomposition, I can define theta sub W as the corresponding composition of recut complexes. Okay, this is defined up to isomorphism. And here's the key idea of all the results I've been talking about so far, which is that for many W, and I'll tell you exactly what I mean by many later, this corresponding functor, theta W, is what's called a perverse equivalence. It satisfies some nice properties. Okay, and I think instead of telling you right now exactly what the definition of perverse equivalence is, I'm going to tell you the two most important consequences of this property. And if you want later, I can tell you the definition. But, let me just tell you what I'm using from this definition, from this property. So here's the key properties, or consequences, not properties. Consequences for this. So if I have some endofunctor theta, let's say dV of A, and this is a perverse equivalence, whatever that means, if theta is perverse, then the following two things hold. One, theta induces some bijection, I'll call phi sub theta, on the set of simple objects in my abelian category. Okay, so here, ver A is my notation for simples in A up to equivalence, up to isomorphism. Okay, so from one thing I get from a perverse equivalence is some combinatorial thing, some bijection of this set. Now, the other thing I get from a perverse equivalence is that, well, first of all, regardless of it being perverse, just the fact that it's a triangulated functor, it's going to induce an operator, and we call it little t, on the vector space, which is a complexified Grothendieck group. Okay. Okay, so this is just, okay, I haven't said anything yet. Now, this Grothendieck group, it has a canonical basis, namely the classes of simple objects. Okay, so I can consider the matrix of this operator T with respect to this basis, just like I have been doing all along during this talk. And I can do something crazy, which is take the QR decomposition. Then Q is again a generalized permutation matrix. For exactly the bijection from part one. Okay, so this is something that just comes as consequences of having a perverse equivalence. These two facts. Yeah.
So this depends on ordering of the
Yes.
the irreducibles?
Absolutely. So it's something I've been kind of sweeping under the rug. But part part of the definition of saying that this thing is a perverse equivalence, this requires to have some sort of partial ordering on a set of simple objects. And any linearization of that partial ordering is what you have to take when you write down this matrix. You have to do with it. You have to be careful about the order of the. In examples like all the type A examples, I know exactly what it is. But when I talk about other types, like in type A, it's Bruhog.
Okay.
In other types, actually probably is also Bruhog, but I set down right there. Okay. Okay, so this is what we're going to use. You can already see why it's going to be relevant for this problem. So this is the consequences. Now let me just show you kind of a general approach to solving the kind of problems I've been interested in. So what's the upshot here? When we're in the setting where we have a categorical representation of G, or EQ of G, and this regard complex theta W, how do I want to say this? So we say the operator that theta W induces on V sub 0, where V is my notation for just the complexified Grothendieck group of a categorical representation. So I'm just writing V for this complexified Grothendieck group. And so I'm looking at the 0 weight space here. So this, because the braid group action preserves the 0 weights of category, is going to induce an operator in the 0 weight space. Okay? And the operator this that theta W induces on V sub 0 is precisely W, which also acts on the 0 weight space. Said that in a very complicated way. Hopefully that makes sense. So for those W such that theta W is perverse, we have one of these results. We have that if we take the matrix of W, write it with respect to this canonical basis and take its QRT composition, Q is up to sign the bijection corresponding to theta W. Okay, so it's just like a very general schema. Anytime we have a categorical representation, we can ask which theta W perverse. For all those that we have this property, we get one of these results. Okay, so let's just specialize this general schema to some interesting special cases. So special case, let's take lambda, a dominant integral weight of my Lie algebra G. Let's let L lambda be the corresponding irrep of G. Then this has some nice, or I guess in the setting I've been talking about irrep with the quantum group. This has a kind of canonical categorification for 0 to square representations. So let's let curly L of lambda be what's called the minimal categorification of this irreducible representation. Okay, this is, and I mean, what this means, remember, when you have a categorical representation, it has decomposition of these weights of categories. So when I say categorification of L lambda, I just mean that the representation we get in the growth entity group is precisely this irreducible representation. When I say minimal, I mean that the piece of the category that corresponds to the highest weight of the representation is just a copy of vector spaces. That's what that means. And you can there's just a side comment, you can realize these as, or construct these as modules over a cyclotonic Kähler algebra here. So that's just an aside. Okay, so in this situation, let's think about what our results give us. So, okay, so we have this, I'll take the growth entity group, and then again, just focusing on zero weight subcategory. This thing is isomorphic to the zero weight space. Inside here, I have the classes of simple objects, which I call L lambda 0. This gives me some basis here. And in here, there's a nice basis called the dual canonical basis. Originally constructed by Lustig. And these bases agree under this isomorphism. And kind of repeating what I said before, if I take a Ricard complex theta W, it induces some operator on this growth entity group, and this exactly corresponds under this isomorphism to the action of the corresponding element W on this zero weight space. So this whole picture is totally compatible. Okay. All right. Let me tell you. So now the question. So the schema is that now for any element of the Weyl group for which I know that theta W is perverse, I get some interesting information about the action of W on the dual canonical basis. I mean, this whole QR decomposition came. So the question is then which are perverse? Which elements are perverse? So the next theorem answers that question.
So who proved these consequences of perversity?
Sorry?
Who proved these consequences of perversity? Okay.
I mean, it's us, but it's not hard. It's just
Okay.
just observations
Okay.
from the definition. Yeah. So just some notation. Remember, I have my Deacon diagram I, and if I take a subdiagram J and I, let's let W not upper J be the longest element in the corresponding parabolic set. Some notation. Then here's a theorem. So this is again with Gassau, but it builds on work, uses very critically previous work with Eva and Losev and Tony Licata. So what we do is we choose any chain of diagrams. So I have my Deacon diagram I, and let's say it contains I1, which contains I2, and it ends in some I R. Chain of subdiagrams. Then I'll write this then. What I'm going to do is consider the element W, which is the product of these corresponding long elements written in the correct order down the chain. And so I choose any chain of diagrams, and to such chain I can associate an element with the Weyl. And each of these W's, theta W is a perverse equivalence. Okay. And so again, I mean, I said this out loud, but just to drive home the point, therefore, for such W, if we take the matrix of W in a dual canonical basis, and take its QR decomposition, then here's one of these permutation matrices. It says that for these specific elements of the vowel group, we can control in some sense the action on a dual canonical basis, or maybe extract interesting combinatorial information from the action on a dual canonical basis. And now, so that's a special case of this general schema. Let's look at a special case of a special case. Which is that if we take lambda partition of n, before when I started the talk, I said for a partition of n, we can associate an irreducible representation of the symmetric group. But I can also view a partition of n as a highest weight for SLN. So let's let L of lambda be the corresponding irrep of SLN. Then a consequence of Sure-Vowel duality is that if I take the zero weight space of this representation, this is a copy of the spectrum. That's upper lambda. Moreover, the dual canonical basis on the left-hand side corresponds to the cardinalistic basis on the right-hand side. And also, moreover, the permutations. So again, we're in type A, so I can talk about permutations. These are the vowel group is just a symmetric group. So the permutations that can be expressed as these kind of products like this, these are precisely the separable permutations that I defined earlier. Okay, so that shows that theorem that I wrote down before about separable permutations, how we extract that as a very special case of this more general phenomenon. So this is how we prove that theory. And this is kind of a side comment. When we were proving these results, the thing that naturally falls out from our approach is elements that have this kind of decomposition. And my students who are much better programmers than myself, they just started counting how many such permutations you can actually get for the symmetric group. And they put it into this online dictionary of integer sequences, and it has exactly one hit, which exactly counts as separable permutations. And once you have a definition of separable permutations, it's very easy to show that they're exactly the same. Maybe not very easy, but pretty easy. So it's one of those happy coincidences that happens from time to time. So that's actually all I had planned. There's a lot of things like I didn't even define perverse equivalences. I didn't tell you about cactus groups. If there's any details like that you want me to get into, we can get into, but I'll stop here.
Any questions?
Yeah, if you take a permutation which is not an element which is not separable, you know that it does not induce a perverse equivalence.
I don't have that as a theorem, but in examples.
An example.
So sorry,
There are examples of a non-separable thing and a.
Sorry, let me back up. What I said was totally not correct. Not totally correct. Those permutations in S4, which are not separable, you can check that they don't correspond to any permutation under this QR decomposition correspondence under any ordering of the cardinal sequences. Maybe that doesn't on the nose prove that they're not perverse, but I really don't think they are. But I didn't prove that.
Isn't that? Did I misunderstand an earlier statement that if you're perverse equivalence, then you do permute the basis of simples?
Yeah, I guess,
Or-
I mean, yeah, so you're right, so, sorry,
Or-
no, that's what you said is true. You can generalize what you mean by perverse. So if you want perverse with respect to the standard key structure on the Weyl category, then definitely they're not,
I see.
but you might be able to find some non-standard key structure.
Okay.
I mean, I guess you may hint at that. So then, I guess, do you have a vision on like how can you like fix this for I don't mean non-separable or non-perverse. So
Like to try to prove some analogous thing for non-separable
yeah,
elements.
yeah, like savable, I guess.
Not really.
Okay.
I like the feeling I'm getting that this is the right level of generality for this results. Like I don't expect it to hold everywhere. I mean, it fits very nicely into the cactus group picture. So the cactus group is generated by, so it has several definitions. You can take a presentation of this group where the generators are indexed by subdiagrams of your Deacon diagram. And those subdiagrams, yeah, I mean, so we get all these, and so like for instance in type A, these generators correspond to action by partial Schutzenbergian evolutions on known diagrams.
Okay.
And this like fits very nicely to this picture that
Yeah.
we see here with subdiagrams. I just don't expect it to generalize
Okay.
super well.
Where in the story did you use that the Deacon diagram was simply laced?
I hit that. So the way where I used it is where I said I have a categorical braid action. So that's proven in a singular case. And I don't know if this story, I expect it probably will generalize the non-singular case. But just the basic theory hasn't been settled for that.
Maybe this is more of a background question, but these recurrent complexes. So you gave kind of one example of a category with all the kind of actions and morphisms you can describe. Are there other kind of interesting examples that show up? Say in type A.
Like categorical representations.
Yeah.
So the other really interesting class of examples is tensor product categorifications. So those also have, like Lustig also constructed canonical basis there. And we have all the, I mean, I just don't want to get into that detail, but all these results hold for tensor products also.
In this theorem, is the Q equal to this bijection up to a sign or just?
It's up to sign, yeah.
Oh,
Just got music, yeah. And if you want to, so for instance, if you want to understand what is exactly the bijection that you get here, you have to express your W in this form, and then take the corresponding cactus group operators corresponding to all those different subdiagrams. That's exactly the bijection you get.
Any other questions?
Is there a connection to cactus? So I'm trying to distill which of the story is like special to type A. So if you is there a notion of separable in other types? And is it related to the cactus groups, or is it,
Yeah.
or is that a definition, or is that a?
So it's another one of those happy coincidences. So if you look at this theorem, this is a general type, and you can ask like, okay, so here's this. We know in type A, elements of the Weyl group that can be expressed in this form are precisely the separable permutations. So this gives you a definition of separability in other types. And then I was like, oh great, we found a definition of separability for E8. But then it turns out this was defined in papers like 2 years ago. Separable elements of finite Weyl groups. One of the authors is Christian Gates, and so I forget the other one. And they have the exact same definition as far as I can tell. But I haven't looked at it too closely.
Are there canonical bases in prime characteristic or
There's P canonical bases, yeah. Sorry, a prime characteristic where you're looking at Modular
Modular
representation.
representation,
Oh, sorry,
yeah.
canonical bases are different. Are there canonical bases? Not that I'm aware of, but, Griffin?
I have to think about what that means, but these are, if you're, because these bases are coming from like, because your representation, it comes with the natural integral form, which is like the K0 of this category.
Yeah,
I think these bases live in the integral form, so they actually descend to any characteristic that you want. Am I wrong?
yeah, think about that.
There's a chance that I'm saying
What
something.
do you want to do?
Your representations come with it.
Yeah, that's a good point.
Yeah,
But you,
but whether or not they're,
like, would they be preserved and like, would they all survive the extension of scalar? Yes.
I'm not sure what happens when you raise them on P.
Yeah,
They definitely descend to something,
Yeah,
but whether or not.
like with still a basis.
Yeah.
Certainly like the representation theory of SN, you know, modular representation theory of SN is going to be different from the
Yeah, I mean,
Everything's
like,
zero.
so you get a basis of some like representation, but it's not necessarily reducible anymore.
Yeah.
Whether you get a basis of
Yeah,
naturally reducible pieces, not totally. But
yeah. But it's important that because all of this is obtained as a decategorification of some categorified story, you have natural integral forms of everything in sight.
Yeah.
But you know, like, yeah, but as you said, these are like cell modular, or these are like not irreducible. And
yeah,
there's probably all kinds of stuff that I don't know.
thanks to so.
Yeah, well, of course, but.
All right. Let's thank Oded again.
Holding on to these chunks.